Primeiramente, queria dar boas-vindas a vocês aqui no nosso instituto, quem não é aluno aqui da Física. Quem é aluno, continue bem-vindo. Quem não é, bem-vindo ao Instituto de Física. A gente vai fazer uma aula com o professor Daniel Phillips, que é uma aula alegre, uma aula onde tenta se explicar alguns conceitos de uma forma divertida, de uma forma com demonstrações. Tá certo? Nós não contratamos tradução simultânea, porque eu acho que todos vocês entendem inglês, não entendem? Então eu falei assim, puxa, se eu contratar um tradutor, é como dizer que esses alunos aqui de São Carlos não são bons o suficiente. Então eu preferi optar que vocês são bons o suficiente. Então nós vamos fazer aula em inglês. Mas o inglês do Bill é um inglês tranquilo, todo mundo vai conseguir entender bem. Tá certo? Professor Bill Phillips is a very good friend of here. He is an honor professor of our institute, so we can say he is a colleague of the institute. He comes to São Carlos, I don't know how many times. And Professor Phillips did a very nice technique in his life, which was to control the motion of atoms. And that led to a new window of opportunity in physics. Is the exploration of matter very near the absolute zero of temperature. And because of he was a main person in the introduction of this field, he got Nobel Prize of Physics. And the field is still growing. It seems that when we observe matter near the absolute zero of temperature, we understand more and more what's going on around us. Today, the technique that Bill started is being applied to mainly all the fields of science. We believe that even biology, even biological effect, will be better understood if we can use cold atoms as one of the tester, as a detector for like current in the brain. Chris Helmerson, which I don't think is could fit in here. Chris? Chris is a colleague of Bill, worked with him for many years at NIST, is now trying to do things like this. Sensors with those atoms. So you see, condensed matter, field theory, cosmology, all are receiving a big benefit for understanding better using cold atoms. So I think Bill is one of those important persons of the century that let us understand better science with the techniques he creates. So I want you all give a very nice welcome to Bill.
Thank you very much. Thank you. It's always a pleasure to be in San Carlos, and it seems that every time I come here, the excitement about science grows. And I've been in this lecture theater many times, and this is surely the biggest crowd we've ever had. This is wonderful. So I'm here today to talk to you about the marvels of physics close to absolute zero. And there's another title that I use in English, Time, Einstein, and the Coolest Stuff in the Universe. I come from a place called the Joint Quantum Institute, which is a joint institute between the National Institute of Standards and Technology, NIST, and the University of Maryland. And I am part of the Laser Cooling and Trapping Group. And the permanent members of that group, Gretchen Campbell, Paul Lett, Trey Porto, and Ian Spielman, are people with whom I'm privileged to work every day. And it's a real pleasure to work with such wonderful scientists. At one time, Chris Helmerson, who was mentioned earlier, was a part of this group, but he's moved on to Australia. Am I not speaking loud enough? Yeah. Okay. Okay, good. good. Okay, so I just want to acknowledge the fact that we've had support from NIST, from the Office of Naval Research, from the National Science Foundation over the years, and also to mention to you, young people especially, opportunities for research and education at the Joint Quantum Institute. There are lots of fellowships and scholarships available, and so if you have an interest in this sort of thing, you could look into the Joint Quantum Institute. I also want to mention a wonderful lady, Catherine Gebbie, who died this year, just in August. She was central to the formation of the Joint Quantum Institute, and she created an environment that over the span of 15 years produced 4 Nobel Prizes in physics under her leadership, an amazing woman. This is one of my favorite pictures of her in her office with the posters honoring her people. For her, it was always about the scientists that were under her care. And she was a wonderful lady, and I'm so sorry that we no longer have her with us. She died at the age of 84. Okay, time, Einstein, and the coolest stuff in the universe. So, what does time have to do with Einstein? Well, Time put Einstein on the cover of their magazine as the person of the century. And I think it was an excellent choice because Einstein did so many things that changed our understanding of this amazing and wonderful universe in which we live. So many things, and I wish I had time to give a little bit about each one of these things, but probably the thing that Einstein is most famous for is his theory of special relativity. Before Einstein's theory of special relativity, people believed that space and time were like an unchanging stage, like the stage that I'm on which the action of the universe occurred, but the stage didn't take part in the action. Well, Einstein changed that. Boy, you people are really going to be excited by this lecture. Einstein changed all of that by making the stage, time and space, part of the action. He found out, much to everyone's surprise, that the nature of space and time changed depending upon who was looking at it and how fast they were going with respect to other observers. And he came to this amazing conclusion by asking himself a question that I suppose people have asked themselves since the beginning of time. He said, what is time? What is this amazing thing that is always in the present but will soon become the past, that allows us to think about the future, which will soon become the present? The present will soon become how does that work? You see, time is such a strange thing, I can't even figure it out on the fly. The future will soon become the present. So he asked himself that question, and the answer that he gave may seem a bit superficial. He said that time is what a clock measures. But by taking seriously the idea that time is what a clock measures, he came to the conclusion that time itself is something that depends upon who is looking at it. But if time is what a clock measures, you might ask, what is a clock? Well, for me, a clock is something that ticks. Something that gives you a set of periodic events that allows you to tick off days or hours or minutes. The rotating Earth is the earliest clock. Ancient people didn't know that the Earth was rotating, but they saw the sun rise and set every day, and in this way they were able to tick off hours and days. Much later, according to legend, Galileo was sitting in the congregation of the cathedral in Pisa, apparently not paying very much attention to the service, and watching instead the swinging of the chandelier in that great cathedral. And he noticed that regardless of whether the chandelier was swinging a lot or whether it was swinging a little, it took the same amount of time for the chandelier to swing back and forth. Almost exactly the same amount of time. And this began the use of a pendulum as a timekeeper and led to clocks like this one, this beautiful wall clock or grandfather's clock. Some of you who are perhaps a little bit retro might be wearing a clock on your wrist. Inside this quartz clock is a quartz crystal shaped like a tuning fork, and the vibration of that quartz tuning fork is the ticker for that clock. So there are lots of different kinds of clocks. Some of these clocks are absolute marvels of engineering and art, like this beautiful tall clock. But every one of these clocks is imperfect in one way or another. Let's look at our pendulum again. While the period of the pendulum is relatively independent of how far it swings, it is not at all independent of how long the string that holds the pendulum is. So that if you have a clock that uses a pendulum as its ticker, and the length of the pendulum stretches or shrinks, it will change the ticking rate of that clock. Every quartz crystal manufactured for one of these watches is a little bit different from every other one, and it could change its ticking frequency with heat and humidity. Even the rotation of the Earth is affected by things like the tides and storms, ocean currents changing will change the rotation rate of the Earth. Earthquakes change the rotation rate of the Earth. The fact that the Earth is not a constant ticker was made clear to me one day in a dramatic way when I was visiting the U.S. Naval Observatory. Now, the Navy, of all countries, is interested in timekeeping, and so I was visiting a colleague who was going to show me the latest clocks that they had, and as we were walking to his laboratory, we passed by a door, and on the door was written, Director of Earth Rotation. Seems like a rather responsible job. You wonder, what happens if that guy goes on vacation? The point is, somebody keeps track of the variations in the Earth's rotation for people who still navigate using the stars and for people who still want to keep track of the position of celestial objects in the sky. And that is something that has to be reported out by very careful observation because of the fact that the rotation of the Earth is changed by all sorts of things. So all of these clocks are imperfect in one way or another. The best clocks are atomic clocks where atoms are the tickers. So why do atoms tick? Well, as you've probably learned, atoms have very specific energy levels. And the thing that's wonderful about atoms is that every atom of the same kind has their energy levels exactly the same. That is, every cesium-133 atom in the entire universe, as far as we know, is absolutely identical to every other cesium-133 atom anywhere in the universe, which means that those cesium atoms tick at the same rate no matter where they come from. So unlike a quartz crystal, where each one is a little bit different, every cesium atom is absolutely identical to every other cesium atom. And so, if you use cesium atoms as the tickers for your atomic clock, then you can be guaranteed that you've got the right ticking frequency. And the cesium atoms are much less affected by things like temperature and changes in humidity, mainly because we keep them inside a vacuum. They make wonderful, wonderful clocks. Well, so you might ask, how good are these clocks? Well, for less than a few hundred reals, you can get a quartz watch like mine, and it will be good to better than a part in a million, which is 30 seconds in a year. But for around 300,000 reals, you can buy an atomic clock that is good to a part in a million, a part in 10 to the 12, or 30 seconds in a million years. Now you laugh. 300,000 reals, who wants to pay that kind of money for a clock? But think about it this way. You pay 1,000 times more money and you get 1,000,000 times better performance. I think that's a real bargain. But you may ask, why does anybody want a clock that good? After all, Most of us don't need to know what time it is in order to go about our daily lives. Or so you may think. I would now like to convince you that you are very happy that someone is keeping track of time to this level of precision for some very ordinary things that you do. I once found this advertisement in a magazine. It says, if you buy our car, you can relax because if you get into trouble, help is only 10,000 miles away. That's about 20,000 kilometers for people who use ordinary, proper units of measure. The point is that I mean, that's not a very close conversion. But anyway, the point is, this is the approximate orbiting altitude of a constellation of satellites that make up the satellite navigation system, the global positioning system, GPS. And on each one of those satellites are several atomic clocks that are of the precision that you could buy for 300,000 reals. Now, they cost a lot more than ones that are on the satellites because they have to be space qualified and all that. But the point is that it is those incredibly good atomic clocks that makes possible the operation of the satellite navigation system. So here is a cartoon of the satellite navigation system. Here are two satellites which have on board several atomic clocks. And let's imagine that you are sitting somewhere on the Earth and that you also have an atomic clock. You don't. But just for the sake of argument, let's imagine for a moment that you do to understand how this works. Now, all of these clocks are synchronized. You see, all the clocks are showing the same amount of time. And these clocks, the ones in the satellite, are broadcasting what time it is. And remember, they're all at the same time. They're also broadcasting where they are. Now, when they broadcast what time it is, the signal travels at the speed of light from the satellite to the receiver, where you are. And when you receive that signal telling you that the time is 1 in some units, and your clock reads 4, and you know that all the clocks are synchronized, you know how far away the satellite is because you know how fast light travels. And so you know that you're somewhere on this surface. Well, that's a good start, but there are more satellites. And they are all broadcasting information about what time it is and about where they are. So when you get the signal from one of those other satellites, you know you're at the intersection right here, and that's how your GPS can tell where you are. Essentially anywhere on the face of the Earth to within a few meters. Now, what happened there? Okay, so you don't have a clock on your GPS receiver, so you need 3 satellites to make up for the fact that you don't have a clock. Also, we don't live in a 2-dimensional world. We live in a 3-dimensional world, and so that means you need still 1 more clock. So anytime you can see, that is, anytime your GPS receiver can see 4 satellites, you can figure out where you are. Your receiver can figure out where you are. So that's how the global positioning system works, and people use this for everything. People use it to find their way to the store on Saturday night. They use it to find their way around an unfamiliar city. Package delivery people use it to deliver your packages so they don't get lost along the way. Because if they get lost, that takes time. And of course, we know that time is money. So they don't want to lose any time, and so the way they do that is use the time that comes from the global positioning system. Now you might ask, what do these atomic clocks look like? Well, I found another advertisement in a magazine. It said that recently scientists in Braunschweig, Germany set the atomic clock back 1 full second. This was an ad for an airline, and it says, our flight schedules have been adjusted accordingly. Yeah, right. This airline is no longer in business, but what they said about the atomic clock was correct. Every so often, the atomic clock, the atomic time is adjusted by a second, forward or backward, to make up for the fact that the Earth's rotation is irregular and generally slowing down. And so in order to keep atomic time in step with sun time or stellar time, you need to make adjustments. And these are called leap seconds. You might have even heard about this. The 30th of June, people will say, well, you get an extra second today. Make sure you use it wisely. So on the 30th of June and on the 31st of December is the time when you might add or subtract leap seconds. So they're absolutely correct. Of course, it's not done in Braunschweig, Germany. It's done at the BIPM, the International Bureau of Weights and Measures in Paris. And why an American company would refer to the German standards laboratory in Braunschweig, I have no idea. But as I said, these guys are out of business. But that's not the reason I'm showing you this picture. The reason I'm showing you this picture is to assure you that the instrument in front of which these two dorks are standing looks nothing like an atomic clock. There is no instrument that looks like that at all, except in someone's imagination. But if you were to go to our laboratories in Boulder, Colorado, to look at the real atomic clocks that existed a few years ago, you would have seen an instrument that looked like this. Now, maybe the sign isn't there, but this long apparatus here is an atomic beam. And inside that, you have a stream of atoms going along at a few hundred meters per second. And those atoms are the tickers for this clock. Now, how does that clock work? Well, here is a cartoon of a cesium atom showing two different states of the cesium atom. These states correspond to two different relative orientations of the spin of the electron and the spin of the nucleus. So if the spin of the electron and the nucleus are oriented like that, it's one energy, and when they're oriented like that, it's a different energy. And the difference in those two energies corresponds to a frequency, and that frequency is about 9 billion cycles per second. And in fact, it's exactly this number here by definition. That is what we use to define what we mean by 1 second. 1 second is the time it takes a cesium atom to tick 9 billion, 192 million, blah, blah, blah. That's what a second is. And when you make a clock using a cesium atom, you are making a clock that is using the very definition of what we mean by time. Now, how does it work? You shine in microwaves at this frequency of 9 gigahertz onto an atom that is in one of these states. And if the frequency is just right, the atom will change its state. And if the frequency isn't just right, the atom won't change its state. So you just tune the frequency until the atom changes its state, and then you know that that frequency is this frequency, and then you can broadcast that, and everyone knows how long a second is. Now, I've warned in the title of this thing, this is an oversimplified version. Now let me give you the simplified version. So in the simplified version, we have an atomic beam coming along, and it is irradiated by microwaves. And the longer that these atoms stay in the microwaves, the better things are, because you've got more time to make the measurement. That's the simplified version. Here's something a little bit closer to reality. Here I've drawn the atoms as if they were tiny clocks, which they are. And what happens is that the atoms come into this region where they see the microwaves, and the microwaves get them starting to tick. And they tick at exactly the right frequency. The microwaves are ticking too, but they're ticking at whatever frequency they happen to be ticking at. So you start the atom and the microwaves, and they're on the same tick, and then a few milliseconds later, when you get to the other end of the apparatus, because this apparatus is about 1 meter long, and the atoms are traveling at more than 100 meters per second, so it only takes a few thousandths of a second to get to the other end, then you check to see whether they're in sync. And if they're not, you make a correction. That's how the atomic clock works. So you keep correcting the microwave oscillator to keep it in sync with the atoms, and then you've got a microwave oscillator that's at the right frequency. Now, These clocks are amazing. These laboratory versions of these clocks are 100 times better than the ones you can buy. They're good to a part in 10 to the 14. But the trouble is that we want to do better, but we can't do better because the atoms are moving so fast. The atoms are moving at more than 100 meters per second, and that means there's a limited time that the atoms are in the apparatus. And that limited time means that there's an uncertainty in what the ticking frequency is, which is on the order of 100 hertz. That's 100 hertz out of almost 10 billion hertz. Now, that may not sound like very much, but it's a disaster. It's a part in 100 million, and we want to do a part in 100 million. So that means we have to find out where the center of this broad response of the atoms is to a part in a million. And yet people do that. But that's not all. The atoms are moving. There's a Doppler shift. You know about the Doppler shift. If you're standing by the side of the road and you're listening to a car come by, it might sound like this as it goes by. Because when it's moving toward you, the frequency of the sound is shifted up, and when it's moving away, the frequency of the sound is shifted down. Well, it's the same way with the atoms, and it's the same way with the microwaves that the atoms are looking at, and that's a disaster. This is a part in a million, and we want to do a part in 100 million. Fortunately, there are all kinds of tricks to get rid of that, and the failure of those tricks to work perfectly is one of the things that limits these clocks. And finally, there's Einstein. Einstein taught us that time was relative, and it turns out that moving clocks run slow. The effect is on the order of a part in 10 to the 12. Now, that may sound not so bad compared to the other ones, but we want to do a part in 10 to the 14, and there's no tricks to get rid of this. You have to measure it, and the inability to measure this perfectly is one of the things that limits the performance of these clocks. So what are we going to do? What we're going to do is we're going to make the atoms move more slowly, and in order to make the atoms move more slowly, we have to cool them down. Whoops. We have to cool them down. Because the difference between hot and cold is the difference between fast and slow. The hotter a gas is, like the air in this room, and you people are heating up the air in this room a good bit, the hotter the gas is, the faster the atoms and molecules in that gas are moving. And the colder the air is, the colder the gas is, the slower the atoms and molecules are moving. So if we want our atoms and molecules to move more slowly so we can make better measurements on them, then we're going to have to cool things down. So in order to illustrate for you just how cold we want to get things, let's turn the lights on now. Courtesy of the Institute of Physics here in San Carlos, I've got some really cold stuff. This is where it gets exciting for the people in the front. This is liquid nitrogen. Now, nitrogen is the main constituent of the air. That means that this is essentially liquid air. It is so cold that compared to it, the floor on which I'm standing, the stage on which I'm standing, is burning hot. Red hot. Imagine what would happen if you heated up a stove until the stove top was red hot, glowing hot, and then you poured cold water onto the red hot stove. What would happen? The water would boil. And that's what's happening here when I pour the liquid nitrogen out. Anybody getting cool in the front row? So I'm not sure whether everybody is getting a chance to see this marvelous stuff, but let's just pour a little bit over here for the people on this side, and let's pour a little bit over here for the people on, oh yeah, on this side. This stuff is amazingly cold. And you might imagine that if you've got something this cold, this would be a good thing to use to cool down your gas so that you can slow down the atoms and molecules. So here I have a traditional container for hot gas. So I understand this is one of your university colors. So what we're going to do is we're going to take this hot gas and we're going to stuff it into this bucket, which is filled with liquid nitrogen. So I'm going to put it into this bucket filled with liquid nitrogen. And we're going to hope that if everything works well, the atoms and molecules will slow down. Okay, great. So now what else can I do to show you how cold this stuff is? Well, here I have a thermos bottle. We call this a Dewar flask. It's basically an insulated bottle. It's been sitting out at room temperature all day. And that means that compared to the liquid nitrogen, this thing is red hot. Imagine taking a metal bucket and heating it up in a fire until it was glowing red, and then pouring cold water into the bucket. What would happen? It would boil. Don't try this at home. So while that is boiling away, cooling down the inside of that container, let's cool down some more gas. With a balloon, also one of your university colors, if I'm understanding correctly. So let's stuff this balloon in here. Okay, there we go. Just stuff it right in there. All right, okay, great. Now, let's go over here. This has boiled down a lot, so let's top it up. And now what I want to do is to take this flower, a nice fresh carnation. It's been sitting out at room temperature all day, so that means this flower, compared to the liquid nitrogen, is red hot. In fact, it's even red. Imagine what would happen if you took something like a fireplace poker, a metal rod, and heated it up in the fire until it was glowing red, and then took it out and plunged it into a bucket of cold water. What would happen? It would make the water boil, and that's what's happening here. And it's just boiling away, cooling down the flour. So while the flour is cooling down, let's try to cool down some more. What? You want to have lots of stuff if you're going to do experiments, right? You got to have lots of gas, and we want to have lots of slow atoms. So we're going to cool down more balloons. So we've got plenty. Okay. Okay, there we go. Now, let's come back to our flour. Now, I look in here and I see that the boiling has subsided. That means that the flour has now been cooled down to the temperature of the liquid nitrogen. This flour is frozen so hard that when I pull it out, I can crush it like it was made out of glass. This stuff is really, really cold. And, you know, if you've got something that cold, then it seems perfectly reasonable that you would use it to cool down your gas to make the atoms and molecules move more slowly. Because there's so many reasons why having the atoms and molecules move fast messes up your ability to measure them. So we want to make the atoms and molecules move more slowly. So let's see what else we can do. When you were very young, and some of you are still very young, I'm sure that when you were learning about how to do things in the kitchen, that your parents taught you that you should never, ever put a closed container of liquid into the oven. Well, here I have a container, and here I have some liquid. I have to be very careful pouring this in. Okay. So now I'm going to close it nice and tight. And compared to this entire room is an oven. Let's see what happens. Okay, now, let's look at a few other things. Here is a rubber band. Nice, stretchy rubber band, right? Let's dunk it into the liquid nitrogen. Now, you can't see what's going on here, but it makes the liquid nitrogen boil. But the rubber band is not very big, so the boiling subsides pretty quickly. And when the boiling subsides, that means that the rubber band is cooled down to the temperature of the liquid nitrogen. When I take it out, I can snap it like it was a dry twig. But all I have to do is warm it up in my hands a little bit, and this thing is back to being a nice stretchy rubber band. This stuff is really, really cold. And, you know, when you got something that cold, well, here's another thing. Rubber ball. Nice bouncy rubber ball. Let's see what happens to the rubber ball when we put it in the liquid nitrogen. And while that's cooling down, let's cool down some more gas. I got to be careful not to blow it up too big, because if it's too big, of course, it won't fit. Okay. So, let's see what happened to the rubber ball. So remember how nice and bouncy the rubber ball was? It breaks like it was made out of porcelain. This stuff is really, really cold. And you figure if you've got something that cold, then why not use it to cool down your gas? And of course, that's exactly what we were doing with these balloons. We were trying to use the liquid nitrogen to cool down the gas in the balloons to make the atoms and molecules move more slowly. But there was a little problem that I was getting the idea that some of you had noticed, that the volume of the balloons that went into this bucket was much bigger than the volume of the bucket. And the bucket was already full. So what was going on? What was going on was that these balloons have become as flat as pancakes. They're like Frisbees. Does anybody remember how many balloons I put in? Yeah, there was 5, and they were orange and blue, your school colors. Let me ask you this. How many green balloons did I put in? What about yellow? How about pink? Whew! That's great. What about brown? How about another pink? How about another blue? Well, there's a red. Oh, that's great. Okay. It's getting a little hard to get these out of here. Okay, there's another brown. There's a, okay. Let's see. Oh, fantastic. Oh, that's great. So, you know, I could have put balloons in here. Okay, now people, you're university students. You're not. You see, bouncing the balloons around like that, that's what 5-year-olds do. It's good when you're 5 years old. Okay, so what was going on? What was going on was that the way you cool something down, the way we were trying to cool something down, is we put the hot gas into a container. We cooled the container by putting it in contact with the refrigerator, the liquid nitrogen, and what happened was the gas condensed. The gas turned into a liquid or a solid. You see, if you look over here, this gas did not disappear. It reinflated once the balloon warmed up, right? But when the balloon came in contact with the liquid nitrogen, it condensed. That means the atoms are stuck together or they're stuck to the walls of the container. That's not going to make the kind of clock that you want, because that perfect ticking frequency is for atoms. Wow! Your mother was right. As you can see, not only did it destroy the bottle, it destroyed the oven as well. So don't ever, ever do that. Don't do it with water in a container in your oven. Don't do it with dry ice in a bottle. Don't do it with some mixture of chemicals that generates a gas. Just don't do it. You know, you see me doing all these tricks with liquid nitrogen. You think, oh, wow, that's really cool. I'd like to do that. No. I have been working with liquid nitrogen for over 40 years. And I have had many, many hours of safety training and many, many hours of experience. You can't do this safely unless you know what you're doing. And there are lots of things that I do on stage that aren't evident to you to keep both you and me safe when doing these things. So don't do these kinds of things without having professional training. Let's come back to the atoms. So the problem is that if we cool these atoms down very much, then they will turn into a liquid or a gas and not provide that perfect ticking frequency because they're stuck onto each other or stuck onto to the walls of a container, and so we have to do something else. How are we going to cool something down without allowing it to touch something that is cold? Because that's the usual way we cool things. We have it in contact with something else that is cold. But if we do that, our atoms are going to stick to that, and that's going to nucleate a place where it's going to condense and turn into a liquid or a solid. So how are we going to do it? And the answer, my friends, is light. The answer has been staring at us from the heavens for centuries because since the time of Kepler, people have known that the tails of comets point away from the sun. So if you have a comet coming in from somewhere out in the Oort cloud, as it comes in, the sunlight warms up the dust and the gas that makes up the comet. And the light pushes on that dust and makes the tail, so the tail always points away from the sun. So when the comet comes in, the tail streams behind it, and when the comet goes back out, the tail streams in front of it. And Kepler figured that out from his observations and speculated that the sunlight was pointing on it, and he was right. And now, today, what we're going to do is we're going to use that force that is exerted by light on atoms, to use a laser to push on atoms to make them slow down. And in order to understand how that works, you've got to understand two things. One of them is resonance. The idea of resonance is that if you shine light or any kind of radiation on something, microwaves, as we talked about with cesium atoms, radio waves, the atoms will not absorb that light, and therefore they won't feel a push from the light unless the frequency of the light is just right. It corresponds to one of the frequencies that the atom likes to absorb. Now, most atoms aren't going to absorb light. Look at the air in this room. You can't, because it's invisible. Why? Because the light goes right through it. The fact that we can see one another, the fact that this laser goes through the air and hits the screen, is because the air is transparent. The frequency of the light isn't correct to excite any of the energy levels in the molecules and atoms in the air. But if you make a gas of some other kind of atom, like sodium atoms, the kind that you see in these yellow street lamps, and if you shine in just the right color of yellow, then it will be absorbed by that gas of atoms. But you have to get the frequency just right. For a gas of sodium atoms, you have to get it right, the frequency, which determines the color, you have to get that color right to within 10 megahertz. The frequency of the light is almost 10 to the 15 hertz. That means you've got to get it right to a part in 10 to the 8th, a part in 100 million. You would never be able to tell the difference between two colors that were different by a part in 100 million. But the atoms can easily tell the difference between those two colors because they are so exquisitely sensitive to the color of the light, to the frequency of the light. So that's one thing. That exquisite sensitivity that demands that in order for there to be any absorption, that the frequency has to be just right. That's one point. The other point we've already talked about, the Doppler shift. If I've got a source of waves and I've got an observer moving toward that source of waves, the observer sees the frequency higher than if the observer were at rest. So for example, let's say you're on the seashore and you watch the waves come in, and you could measure how many waves come in a minute. That's the frequency of waves hitting the shore. But if you got into a boat and went into the waves, the frequency of the waves hitting your boat would be higher. That's the Doppler shift for water waves, and it works for sound waves, and it works for light waves. So now we know enough to understand how laser cooling works. And here's the deal. Here is a gas of atoms represented by these green circles. Some are moving to the right, some are moving to the left in this simplified one-dimensional version. And we have a laser beam here that is tuned a little bit below the resonant frequency. So the atoms don't want to absorb this light because it's a little bit too low in frequency. But this atom, moving like this toward this laser beam, sees it Doppler shifted up, and therefore it wants to absorb that light, and when it absorbs the light, it slows down. This atom, on the other hand, going this way, looks back and sees that the Doppler shift is down and the frequency was already too low, so it will not absorb the light very much going this way. If it did, you see, it would speed up, but it doesn't do it. So going this way, it slows down, and going the other way, it hardly speeds up. But now, just bring in light from the other side, and now this atom sees this laser beam as having the right frequency, and it slows down. This atom sees this laser beam having the right frequency, and it slows down. No matter which way the atom goes, it picks out that laser that is opposing its motion as being the one that it wants to absorb. And now you can just bring in light from top and bottom and backwards and forwards. And now, no matter which way the atom goes in 3 dimensions, it will absorb from those laser beams that will tend to make it slow down. And when Steve Chu and his colleagues at Bell Labs in 1985, Steve Chu, by the way, was the Secretary of Energy during the first Obama administration, figured this out in 1985, they realized that the atom was behaving as if it were in a viscous fluid, and they called it optical molasses. And the name sort of stuck. But that's not the end of the story. If that was all there was, the atoms would simply come to rest. They don't. And they don't because there's a competition between the heating that happens in this process and the cooling that happens in this process. So imagine that I'm an atom and I just happen to be at rest, and there's laser beams coming from the left and from the right. And when I absorb light from the laser, I absorb it one particle of light at a time, one photon at a time. Now, it was Einstein who told us we should think about light this way, that we should think about light as particles. And this has profound effects, because if I'm going to absorb the light one particle at a time, then that means it'll be either from that direction or from that direction, but it's random if those two light beams have the same intensity and the same color. So let's say that I happen to absorb from that side. Now I get a kick. And if I'm a sodium atom, I'm moving now at 3 centimeters per second from the kick from that photon. And I'm excited. Can't you tell? And I want to get rid of that extra energy, and I do that by shooting off a photon. And it's just like shooting a gun. Boom, I recoil back by 3 centimeters per second. I'm ready to absorb again. Maybe I absorb from that side, and now I get another kick in this direction. And then maybe I radiate in that direction, and I get a kick in this direction. So what's happening is the atom is getting a series of random kicks, and that heats it up. But as soon as it starts wandering off in one direction, the Doppler shift guarantees that that velocity will be damped, that velocity will be reduced, because I'll absorb more from the laser beams that oppose the motion. So this balance between the two processes of cooling and heating leads to an incredibly low temperature. These sodium atoms are predicted, based on that idea that I've just explained to you, to reach a temperature of 240 microdegrees above absolute zero. 240 microdegrees above absolute zero. What is absolute zero? Absolute zero is the coldest temperature you could possibly have. Why is there a coldest temperature? Well, what is temperature? Temperature is about motion. In fact, temperature is simply a measure of the kinetic energy of the atoms and molecules that make up the stuff that you're measuring the temperature of. So if temperature is a measure of kinetic energy, what's the lowest kinetic energy you can have? Zero. And when the kinetic energy is zero, that is when the atoms are stopped, then you're at absolute zero. Now, it turns out it's not that simple. There's little details having to do with Heisenberg's uncertainty principle and quantum mechanics. But leaving that aside, let's say just between us friends, that absolute zero is when the motion stops. Room temperature is about 300 degrees above absolute zero. Liquid nitrogen, which I'm guessing, unless you have been in a low temperature physics lab, this is the coldest stuff you've ever seen. It boils when I pour it out on the ground. It makes rubber bands turn into dry twigs. It makes racquetballs turn into, pieces of china. It is 77 degrees above absolute zero. And unless you've been in a low temperature physics lab, the coldest stuff you've ever seen. We get down to temperatures of, we are predicted to get down to temperatures of 240 microdegrees. That's 300,000 times colder than liquid nitrogen using laser cooling. Well, can we do it? Here is a picture. Let's turn these lights out right now. Here is a picture from our laboratory. So let's turn out this row of lights right here so we can see these pictures better. These are laser beams coming in from all directions. This is a cloud of sodium atoms. There's about 100 million sodium atoms in there. It's about 1 centimeter across. And the theory predicts that the temperature could be as cold as 240 microkelvin. Now, how are you going to measure the temperature of something that is 240 microdegrees above absolute zero? It's not like you could take a thermometer and stick it up into the gas and find out what the temperature is. You have to go back to what temperature means about velocity. So here is how Steve Chu and his colleagues did it. They put the atoms into what we call this optical molasses. The atoms are jiggling around, and they're being slowed down constantly and heated up constantly by the laser beams, and then you suddenly turn the laser beams off. The atoms have whatever velocities they have. They fly apart just like any gas would expand in a vacuum, and after a few thousandths of a second, you turn the laser beams back on, and the atoms are stuck again by this, this molasses force. They did that, and wonderfully, they found that the temperature was 240 microkelvin. There was a big uncertainty because this is a hard experiment to do. But this was wonderful because this is exactly what the theory predicted for the lowest possible temperature, and they got it in this first experiment, 240 microkelvin. We repeated those experiments a little while later and did it in exactly the same way and got exactly the same answer. So that was great. And other people did other measurements with different atoms where you predict a different result, and they got results that were consistent with what the theory said. So everyone was happy until we started to make some more measurements. We were trying to measure how sticky the molasses was, how rapidly the velocity of the atoms was changed, and it was not consistent with what the theory said. So we thought, well, we'd better remeasure the temperature to make sure we understand what's going on, because after all, the temperature measurement wasn't very good, and maybe if we measure it better, we'll get a clue as to what was going on. And in fact, we did. In 1988, quite unexpectedly, we measured that the temperature was much colder than had been predicted. In the first experiments that we measured, the temperature was 6 times colder than what the temperature was predicted to be. Now remember, the whole point of the experiment was to make the atoms as cold as we could. We had apparently made the atoms colder than we could. And this is obviously a violation of Murphy's law. And physicists believe in Murphy's law almost as strongly as they believe in conservation of energy. So we felt a lot like the poor devils in this cartoon who have seen something that is way too cold for the environment in which they're living. And I want to mention that this cartoon was drawn by Chris Helmerson, whom Vanderlei talked about a little bit earlier. And so we found 4 different ways of measuring the temperature before we went public with this idea that the temperature was below what the theory had predicted. And then other people confirmed our experiments, and now there were a lot of discussions about the theory, because obviously the theory was wrong because it was predicting the wrong results. And I wish I had the time to tell you about the new theory that emerged, but using that new theory and guided by that new theory, we were eventually able to get cesium atoms cooled down to 700 nanokelvin. That is 7/10 of 1/1,000,000th of 1 degree above absolute zero. This stuff, liquid nitrogen, which is the coldest stuff you've ever seen. Ah, it's so exciting in the front row, isn't it? Is 77 degrees above absolute zero. We got down to a temperature that's 100 million times colder than the coldest stuff you've ever seen. 100 million times colder. The thermal velocity of the cesium atoms, and remember, cesium is the atom that we use to define what we mean by time. The thermal velocity of these cesium atoms is less than 1 centimeter per second. So instead of greater than 100 meters per second, it's less than 1 centimeter per second. Here is a picture of a clock out in our atomic clock laboratories in Boulder, Colorado. Don Meekoff and Steve Jeffords have laser-cooled cesium here. They toss the atoms up in the vacuum about 1 meter high instead of having an apparatus 1 meter long. And you notice what happens if you toss something up 1 meter high? It comes back down after about a second. So instead of a few milliseconds, you've got a whole second that the atoms are in your apparatus. And that has made all the difference. Plus the fact the atoms are going so slowly, all the other effects have nearly gone away. So these clocks are now operating at an accuracy that is on the order of 10 to the minus 16. That is 1 second in 300 million years. These are the most accurate primary time standards that have ever been made. And primary time standard means cesium, because that's the definition of the second. But that's just the start. Dave Wineland, who got a Nobel Prize in 2012, used a single trapped ion, a charged atom, and an optical transition. Optics plays such a key role here. Using a frequency ticking near 10 to the 15 hertz instead of near 10 to the 10 hertz was able to break the barrier of accuracy in the 10 to the minus 18 level. His clock with a single ion was at about 8 times 10 to the minus 18. Now, it's not cesium, so it's not a primary standard, but now we're just getting started because his colleague out in Boulder, Junyi, takes thousands of laser-cooled neutral strontium atoms held in an optical lattice. Again, optics is key, and using an optical transition has made the best clock yet. It is good to 2.4 times 10 to the minus 18. That is approximately 1 second in the age of the universe. At the National Institute of Standards and Technology, an agency of the United States government, this is what we call close enough for government work. But now you might ask yourself, where do you store the coldest stuff in the universe? What kind of a container can you keep it in? Because we've already seen that if you have a cold container, then your gas is going to stick to it. Imagine this is the container you want to hold your atoms in. And the atoms could be in this container. But if this container were cold, then the atoms would just stick, and they wouldn't be useful for a clock anymore. But if the container was hot, then what would happen is that the atoms and molecules inside the walls of the container would be jiggling around. They would transfer that energy to the atom and heat up the atom, and it would be gone from the container. So you can't use a cold container. You can't use a hot container. Apparently, you can't use any container at all. You can't use a container that is made out of material. Instead, we're going to make a container made out of magnetic fields. So let's go to this camera right here. You remember when you were young, and some of you are still young. Do you remember playing with magnets? Do you remember the first time you held two magnets in your hand and turned the right way and felt that they pushed each other apart without touching? That's what magnets do. You can push on one magnet with another magnet without touching it. Wasn't that an amazing feeling the first time you did that? I'm still amazed by that. And we're going to use that force that you can exert on one magnet with another to trap our atoms. Now let's go over to the other video camera. What I've got here is, in this black base, I've got a big magnet. And what I have here is a little magnet. Now, the little magnet represents our atoms, because it turns out that the atoms that we've been talking about are like little tiny magnets. And this big magnet has been arranged to push up on the little tiny magnet to make it float. And if I held the little tiny magnet right here and release it, it should just float. So when I do that, watch what happens. It doesn't float. It flips over and gets pulled down into the magnet. Now, if you ever tried this when you were a kid, that's what always happens. Whenever you tried to make one magnet float above others, it never works. It turns out there's a theorem that says that it can't work. But there's a way out. You also learned when you were a child playing with toys that if you spin a top, it doesn't fall over. And it turns out that not only are our atoms little tiny magnets, they are little tiny spinning magnets. So I'm going to spin this thing, and now I'm going to lift it to the place where gravity cancels out the effect of the magnet, and the thing should just float. Of course, any two-bit magician can make a woman levitate and then pass a ring around her, carefully avoiding the wires that are holding her up. But you've never seen a magician do this. You see, this is the real thing. This thing really is levitating. Thank you. Now let's go back to the laptop. That was the toy version. And let's turn out these lights. That was the toy version. Here is the real thing. This is a cloud of cesium atoms about 2 millimeters across, cooled down to a temperature of about a microkelvin, and it's been released into a magnetic trap similar to the toy version that I showed you. And since it was released a little bit off center, it's bouncing back and forth. And as time goes on, the imperfect vacuum, the leftover atoms in the imperfect vacuum that we've got, hit our atoms and knock them out of the trap. So that's the way we trap atoms using magnetic field. And over time, we've made our vacuum better so that we can hold our atoms for longer periods of time. We can hold them for minutes instead of for seconds. And using a new technique of cooling, another technique that allows us to get even colder than laser cooling, called evaporative cooling, we've realized one of Einstein's strangest ideas from the early part of the 20th century. Now, what is evaporative cooling? When you want to cool down your coffee, you blow on it. What is happening? The most energetic water molecules are leaving, and what's left behind has less energy on average, and that means it's colder. We do the same thing. We allow the most energetic atoms to escape from not our coffee cup, but from our magnetic trap, and we get them even colder than is possible with laser cooling. Back in 1924, Einstein predicted, based on some new work by Satendra Bose, that if a gas of atoms like ours, cesium atoms or sodium atoms or potassium atoms or rubidium atoms, was cold enough and dense enough, something wonderful would happen. That there would be a phase transition where a large fraction of the atoms would simply stop moving. Now today, we know that they don't actually stop moving because of Heisenberg's uncertainty principle. But in 1924, Einstein didn't know about Heisenberg's uncertainty principle. And when he did, he didn't much care for it. But he came up with this wonderful theory, which later he thought must be crazy and couldn't possibly be true. But it is true. And using first laser cooling and then evaporative cooling in 1995, over 70 years after Einstein's prediction, teams in Boulder, Colorado, our NIST laboratories there, and at MIT and Cambridge, Massachusetts, got Bose-Einstein condensation in a super cold gas and opened up a whole new field of research. Here is a picture of a series of velocity distributions as they approach Bose-Einstein condensation. Eric Cornell, Wolfgang Ketterle, and Carl Wyman got the Nobel Prize for doing that. And now this is being done in great laboratories all over the world, including here in San Carlos. These are pictures of some wonderful experiments being done in Vanderlei Bagnato's group using Bose-Einstein condensates. Well, we're coming to the end of the lecture. We've been on an odyssey of getting colder and colder temperatures, and that odyssey is represented by this cartoon of a thermometer, a logarithmic thermometer that has a tick mark every factor of 10 in temperature to give you an idea of how incredibly cold the temperatures are that we have gotten to. So I've made the top of this thermometer be the surface of the sun. It's not the hottest thing there is, but let's face it, the surface of the sun is pretty hot. On this scale, room temperature is just a little bit cooler than the surface of the sun. And liquid nitrogen, the coldest stuff you've ever seen, something that will boil when you pour it out on the ground. Only a little bit colder than room temperature. Outer space, the coldest temperature that is naturally occurring in the universe. The leftover radiation from the Big Bang 14 billion years ago is at a temperature a little bit less than 3 degrees Kelvin. It's just a little bit cooler than the surface of the sun. The first experiments on optical molasses were colder compared to outer space than outer space is compared to the surface of the sun, and that was just the beginning. Subdoppler laser cooling got even colder. Bose-Einstein condensation and evaporative cooling have now gotten down to 1/2 of 1 billionth of a degree above absolute zero, even a little bit colder. And we have plans for taking these kinds of experiments into outer space in the International Space Station and maybe getting another factor of 1,000 colder. Where is all this leading? Just amazing, amazing things. One of the new and amazing things that's happened is not just cooling bosons, one of the 2 kinds of particles there are in the universe, but cooling fermions. Debbie Jin out at NIST in Boulder has cooled quantum gases of fermions, completely changed our research directions, produced all kinds of wonderful new things. At the age of 47, Debbie died of cancer, having completely changed everything about our research directions. Changing the kinds of things that we can do. Better clocks, some of them using fermions because of what Debbie taught us. Tests of the fundamental understanding of nature, using these clocks to test Einstein's theory of gravitation, for example. Quantum computers, quantum simulation with both fermions and bosons, and more. Maybe the more is some of the things that the young people in this audience are going to be thinking about. And if you are, then maybe you'll be joining a research group like mine, where people from all over the world are gathered together to explore these wonderful mysteries of nature. And you can do that right here in San Carlos. Here's the group of Vanderlei Bagnado a couple of years ago, of people doing that same kind of thing, using these extremes of ultra-low temperature to probe some of the most significant mysteries of the universe. And so we come to the end, but it's never really the end, because there's always something new to learn. Thanks very much. Thank you so much. I just love being in San Carlos, and you people are fantastic. And I know that it's getting late, and some of you may have to leave, but I am happy to answer any questions you have, and I am so eager to have your questions that everyone who asks me a question will get a prize. So, now I think that in order to hear the questions, we may have to pass out microphones.
Questions?
But please raise your hand if you've got a question,
pergunta?
and we'll try to hear it.
Você pode perguntar qualquer coisa.
Yeah, okay, that's a really good question. Now, what we need to do is to have you hand this back to that gentleman. Now, what he's getting is a wallet card of the fundamental constants of nature. So on here, you've got the speed of light, you've got Planck's constant, you've got the charge of the electron. How could anybody be without this? You definitely want to get one of these. Okay, so the question is, how long can you keep something cold? This is such a really wonderful question. Normally, if we cool down something, some material, to a really cold temperature, we have to keep it isolated from the rest of the environment in order to keep it cold. That's why we have things like thermos bottles. Our atoms are kept cold sitting out in the open. We have room temperature light, radiation, infrared light coming from room temperature, bathing our atoms all the time, and it doesn't heat them up the way it would if this was an ordinary material. Why? Because the atoms only absorb light over a very narrow range of frequencies, and there simply isn't enough energy in the room temperature radiation to heat the atoms up. Our atoms stay cold for as long as the vacuum, the imperfect vacuum, allows them to stay around. So basically, we have room temperature background gas atoms. They hit our cold atoms, and it's not so much that they heat them up, they just knock them out of the trap. So that's the limitation on how long we can keep our atoms cold. Now, will we be able to do better in space? Turns out that low Earth orbit is not a very good vacuum. We're going to have vacuum pumps up there, just like we have on Earth, and they're not going to be any better. So we're probably not going to hold our atoms any longer in space than we will on the ground. But here's the difference. When we let go of them, they won't fall. And that makes all the difference, because our atoms fall exactly the same way that rocks do. So if you want to study those cold atoms and you want to turn off the trap so you can study them without the trap on, they're just dropping right down. But in space, they'll just stay there. And they may stay there for 1,000 seconds if we had a vacuum good enough. And we're going to work on improving that vacuum. We only have to improve it by another factor of 10 to get to 1,000 seconds. So that's where that's going.
Como que se fez aquela fumaça?
He wants to know how you made the smoke.
How we make the smoke. Okay. So not only does he get a card, but he also gets a ball. The smoke, and you're going to have to translate for him. Right, you'll translate for him. The smoke is a cloud, just like the clouds in the sky. The way the clouds in the sky form is that hot, humid air goes up and gets cold, and the water in the air condenses into little tiny drops, and that makes a cloud.
Okay.
Here we do exactly the same thing, making the air in the room cold, so that the water vapor in the air in the room
Esse cara adora nitrogênio.
condenses into a cloud. And so we're just seeing an ordinary cloud. And of course, the people in the front get very excited by getting a little bit cold.
Okay, his mother translates for him, so.
Perfect. Okay, I think I saw a question in the back.
Question
There's
in
a
the back.
gentleman back there, and we're going to have to send this. So
Card?
just yell your question out, and I'll do my best to answer it. Ah, yes, why cesium? Well, this was an amazing story
Price.
Se alguém puder
because
repetir,
cesium was chosen.
Why cesium is used as a standard of time.
Right. Why was cesium chosen? That happened in 1965, just a few years after we had lasers and long before we had laser cooling. They chose cesium. Why? Because it had a high frequency. The frequency of about 9 gigahertz is higher than the same frequency in hydrogen, which is only 1.4 gigahertz, or in sodium, which is 1.7 gigahertz. And why do you want a high frequency? Because if something messes up your frequency by a constant amount, then if the frequency is higher, it's a smaller fraction. So that's good. The other thing is cesium is one of the heaviest elements. So that means for the same temperature, the cesium atoms are moving slower, because the kinetic energy is 1/2 mv squared. So if m is bigger, v is going to have to be smaller for the same kinetic energy, which means the same temperature. Also, you don't have to heat cesium up very much in order to make a vapor. So it doesn't have to be so hot to begin with. And cesium is one of the easiest atoms to detect before we had lasers. There are certain metals, when a cesium atom hits that metal, the metal sucks the electron out of the cesium atom because it's so weakly bound. And then you have an ion, a charged atom, and that charged atom is really easy to detect. So all those things were in favor of cesium, and that's why it was chosen. Then it turned out that cesium was one of the best things to laser cool. That was just a gift from God. But there's only one problem with cesium. The collisions between cesium atoms are really bad. So they shift the frequency, and so you have to keep the density very low in order to make a good cesium clock. Turns out rubidium is almost perfect in that regard. It hardly has any collisional shifts, and it's only a little bit worse than cesium in all those other ways. So people are now moving toward rubidium as a microwave clock, but they're moving towards strontium and aluminum as optical frequency clocks, and that's what's going to take over as the definition of time sometime in the future. So,
the temperature, the minimum temperature of 240 nanokelvin was the microkelvin was the lowest temperature predicted by the theory.
By the theory that I told you
Do you know the reason
about.
why the temperature got even lower
Oh
today?
yeah, we know exactly why. But I didn't have time to tell you. So now I'll give you a 1-minute explanation, which you won't find very satisfying. The old theory imagined that the atom only had 2 energy levels, the ground state and the optically excited state. So the atom would be absorbing a photon when it was in the ground state and go to the excited state and decay back down to the same state it came from. Everybody knew that the atoms were not that simple, And everybody thought it didn't matter that they were more complicated. In fact, it does matter. The fact that there are lots of different energy levels corresponding to different orientations of the spin of the electrons and the nucleus in the ground state makes all the difference in the world and gives a new kind of cooling process that gets the atoms much, much colder than was possible with the kind that I described. And we're just going to have to leave it at that because it's beautiful, but it's a little bit more complicated than a 1-minute answer. Yes?
According to Einstein's theory, you said if a gas reaches a state when they will stop moving, the magnetic field will attract the gas, right?
Okay. So you're referring to Heisenberg's uncertainty principle and what happens to a gas that is cooled to absolute zero. Because what I said was, actually I don't think I said it clearly, so I'll say it clearly now. Even at absolute zero, because of Heisenberg's uncertainty principle, the atoms do not stop moving. And the reason that they don't stop moving is because we have them in a trap. Now, why does that make a difference? Because Heisenberg's uncertainty principle tells us that the uncertainty in the momentum, which is the mass times the velocity, times the uncertainty in the position can never be smaller than some number, which is Planck's constant. Now, if we have the atoms in a trap, that means we know where they are. So there is some limited uncertainty in their position. That means there has to be some non-zero uncertainty in their momentum, so they can't be stopped. If they were stopped, there would be no uncertainty in their momentum. Now, if we were to allow the atoms to occupy the entire universe, then we could make their velocity be so small that it wouldn't matter anymore. But in fact, we confine them to a distance of a few hundred microns, and that means that they have velocities that turn out to be on the order of a few microns per second just because of the uncertainty principle. And it doesn't matter how we confine them, whether it's a magnetic field or an optical field or just an ordinary box. If we could find a box that would do that trick, Heisenberg's uncertainty principle will apply just the same.
Hello. So you really like to cool things down, right?
Yes.
But how about heating them?
How about heating things? Well, this is really...
there an upper limit, maybe?
Okay, so there's two questions here. One is there an upper limit to heating things? And the other is, what about using this technique to heat things? There's a really interesting story. It turns out that a lot of the early work on laser cooling was done by people who were trying to figure out how to heat things. They wanted to heat gases that would be used in plasmas for thermonuclear fusion. Well, it turns out that it's easy to heat things with a laser, just not easy to heat them very much. You see, let's say you start at room temperature and you cool it down, taking away all that energy. Then you've really got something. It's almost absolute zero. If you go the other way, all you've done is double the temperature. That's not very interesting. So it never really worked as a good way of heating stuff. But now the other question you ask is really a subtle one. Is there a limit to how hot you could make something? Now, at first glance, you might say no, because you can just put more and more energy into something. And even though relativistically, the velocity of the atoms isn't going to get higher than the velocity of light, it still has more energy, so the temperature will be higher. But then you might ask, well, wait a minute, though. The universe is finite, so there's a finite amount of energy that we could have available to put into these atoms, and maybe that's a limit. On the other hand, you might say, well, maybe if the energy gets that high, maybe these atoms are going to break apart, and they won't be the atoms that we're thinking about anymore. And then maybe I should be thinking about a gas of protons and neutrons. And maybe even those would break apart into quarks. And then maybe I should think about a gas of quarks. And so the answer is not clear. People have been thinking about the question you've asked, and it's not clear what the answer is, whether there really is an upper limit of temperature.
Okay, we have one more question.
Do you think we can reach 0 Kelvin one day?
So, This is a question that always comes up. Can we get to absolute zero? Some people have formulated what's called the third law of thermodynamics, which in some form says you cannot get to absolute zero. Okay, so why is that? Why do people believe that you can't get to absolute zero? Well, let me use it as an example, the laser cooling process that we've just described. The process there involves cooling the atoms down with light, but there is an inescapable heating process that happens that you can't avoid. You have to have that heating process or the cooling process won't work. So you can try to make the cooling more effective compared to the heating, but you cannot eliminate the heating. So that means that you could maybe make the temperature colder, but never get it to zero, because there's always a competition between the heating and the cooling. Now let's think about something else. Evaporative cooling. So we let the most energetic atoms escape, and what's left behind is colder. How do we get it colder and colder? By letting more and more things escape. By the time we get to absolute zero, everything is gone. So we're not going to get to absolute zero that way. Another way of cooling things is by having them expand. We call that adiabatic cooling. Well, the bigger we make it, the colder it's going to get. If we want to go to absolute zero, we have to expand it to infinity. So that's not going to work. So there's always something that prevents us from getting to absolute zero. And one of the things to keep in mind is that if you're talking about temperature, you really have to be talking about a sample that has an infinite number of particles. I could easily take one atom, not a very big system, right? And 99 times out of 100, I can do a process that will put it into the ground state, which is the lowest energy possible. And you would say, well, for those 99 times, it's at absolute zero. And I don't know, that's not what temperature means. Temperature is an ensemble property. So what it means is if I had 100 atoms, 99 of them would be in the ground state and one of them wouldn't be, and that would be the non-zero temperature. So it doesn't appear that there's any way around it, but more and more clever ways get us closer and closer to absolute zero, and that's what we're trying to do for any number of reasons. Better clocks is only one of them, but better understanding of quantum phenomena is a more important one for wanting to get those temperatures colder, so we're still working on it.
You said that you trapped the cloud of atoms with lasers, and it keeps absorbing and emitting photons.
Yeah. Now, they're not actually trapped in that optical molasses. They're sort of detained. We do trap them, but when they're absorbing and emitting photons, it doesn't result in trapping just from that process. It just slows them down and keeps them around for a while.
Yeah. Okay. They keep absorbing and emitting photons.
Right.
Why does that? I didn't get why that cools them down.
Yeah. What? Because, I mean, I'm really glad you asked that question, because let's face it, this whole idea of laser cooling is absolutely ridiculous. I mean, you shine light on something, you expect it to get hot, right? So how is it that we can shine light on something and make it cold? Well, I gave you this argument about how the Doppler shift is going to make the atoms more preferentially absorb, and that's one argument that's a perfectly good argument. But let me give you another one. Because of this Doppler shift, the light that the atoms absorb is always a little bit lower in frequency than the light that they emit. And that extra energy goes into the emitted light, has to come out of the kinetic energy of the atoms, and that's how the cooling process works. Why doesn't it work for ordinary things? Why do you feel warm when you go out in the sun? Because your absorption of light from the sun is broadband. Your skin doesn't really care what the color of the light is. It absorbs it over a broad band of frequencies, and therefore you can't use this trick of having the atoms preferentially absorb from the light that's opposing their motion.
I know that you all have more questions, but maybe you want to chat with Bill a little bit, take a picture, shake hands, so that, show that you appreciate his lecture. Everything that is good in life takes the time enough to be unforgettable. And those are the visits of Bill to São Carlos. But you know, we like Bill so much, and we like the mathematician so much, that this is not the end. Tomorrow, we have another talk of Bill, a little different.
Well, not really a talk, a
about
conversation.
research and the production of new researchers. Amanhã, lá na matemática, às 10 horas, o professor Lidelbrando, que está aqui, estará promovendo uma conversa do Bill com os alunos sobre pesquisa e a formação de novos pesquisadores, e aqueles que quiserem podem ir e fazer as perguntas. Look.
Don't forget about Monday and Tuesday.
Oh, yes, Monday and Tuesday of the week after, we'll be here too. And in Federal University, Rodrigo, Raul is not around. There will be another talk at the Federal University in the physics department, so you can also go. And we'll be here. You know, Bill is here until 23rd of November. Look, I want to thank you, Bill. Wonderful, as always. And everybody appreciate that. And we're gonna stay a little bit here so you can come. As I said, if I was a student, I want a picture to show that I'm a friend of Bill. So you have a chance. Just come. Thank you, Bill.